Calc 1, when you were learning the rules for integration or antiderivatives, there was no rule for an antiderivative to undo the product rule. Well, integration by parts is that rule. So, just a review of the product rule. The derivative with respect to x of f times g is f times the derivative of g plus g times the derivative of f. Now, just to be consistent with how we like to memorize this, I'm going to change these to u and v. So derivative with respect to x of u times v is equal to u times v primed plus v times u primed. Now let's think if we plot an integral on all of this. So the integral of a derivative would just be u times v is equal to the integral of u times v primed, which I'm going to call dv, plus v du. And then we rewrite this u times dv is equal to u times v minus the integral of v du. So I just subtracted the integral of v du from each side. And this is the rule for integration by parts. So you have a product here. A u and a dv. And you're going to choose those. So it's another level of substitution. You choose not just a u like you did in u sub, but also a dv. You want your u to be easy to differentiate. And you want your dv to be easy to integrate, because you're going to need to figure out what u and v are. Well, you know what u is. You're going to need to figure out what v is, and you're going to need to figure out what du is, so that you can plug it into the formula, which this is the official formula for integration by parts. So here's the pretty explanation. There it is with f's and g's, and then there it is with u's and v's. So let's look at a real live example, put some numbers in there and make more sense. So example 1, we want the integral of x times sine of x. If you have a plain old x, that's probably going to be a good choice for you, because then du is just equal to dx, and sine is super easy to take the antiderivative of. So I'm going to let u be equal to x. So du is equal to dx. I'm going to let dv be equal to sine of x. Then v is equal to the antiderivative of sine, which is, don't forget that it's negative cosine. If you want to write this down over and over again to help you remember it, integral of u dv is equal to uv minus the integral of v du. I really can write u times v. So u dv, u times v, I'm going to put the minus out in front, x cosine of x, minus the integral of v minus cosine of x du, which is just dx. So minus x cosine x. I have minus minus, so plus the integral of cosine, which is sine of x, plus a constant. Now, you don't believe it? Then go backwards and make sure that it works. I don't want to put this in my notes, so I'm going to pause and get a whiteboard to do it on. So I got this for my answer. So let's do the derivative. It would be first d second. Derivative of cosine is negative sine plus second. D first. Derivative of minus x is minus 1 plus the derivative of sine is cosine. So I have cosine x minus cosine x, and minus minus is x sine of x, which, oh, look at that. That's exactly what I started with. So, yeah, we did it right. Now pause, do the practice problem, and then we'll go through it together. We're going to do the same thing. Choose a u and a dv. U is going to be equal to y because that's super easy to find the derivative of. Du is equal to dy. And then dv is equal to e to the 0.2 y dy, which means v is equal to e to the 0.2 y over 0.2, because when you differentiate, you multiply by the coefficient of the exponent, and when you anti-differentiate, you divide. So this integral is going to be equal to u times v. So just to make life a little easier, let's do 0.1 divided by 0.2. 1 over 0.2, that's just 5. Yeah, I should know that. So 5 times y times e to the 0.2y minus the integral of v. So again, I'm going to stick a 5 there instead of 1 over 0.2 e to the 0.2 y dy. Easy enough. So I have 5y e to the 0.2 y minus. This integral is going to be the same as my v, e to the 0.2 y over 0.2. And just 5 times 5 is 25 e to the 0.2 y plus a constant. So nice, simple problems where you have something that looks like a product. You let u be equal to one of them, v be equal to the other one. The next type of problems are product rules in disguise. So just the natural log of x. We don't know how to find the antiderivative or integral of that thing, but we can use integration by parts to do it. Which brings us to Lie 8. When it comes to choosing your u, you follow this little acronym here. Logs, inverses, let's see, logs, inverses, algebra, trig, and then exponential. So if you have a log function, that's got to be your u, because you don't know the antiderivative of it. If you have an inverse trig function, That's going to be your u, because you don't know an antiderivative of it right off the top of your head. It's not something that's in a table that you have memorized. So let's look at example 2. We want the integral of natural log of x dx. U has got to be equal to the natural log of x, which means du is equal to dx living on top of x, which means dv has to be equal to dx, which means v is equal to x, because we have to take the antiderivative, go backwards. So this is going to be equal to u times v minus the integral of v du. So x times the natural log of x minus the integral of just dx, which is x times the natural log of x minus x plus a constant. Again, if you're dubious, let's take a quick look at the derivative with respect to x of x ln of x minus x. So first, derivative of natural log is 1 over x plus second times the derivative of first minus the derivative of x is 1. Well, this cancels with that. So I have 1 minus 1 disappears. ln of x. Yeah, we did it right. We got the right answer. And here's all the pretty solutions. And lie 8, inverse function. If we have inverse cosine, then we're going to have to let u be equal to inverse cosine. So try it on your own and then come back and we'll go through it together. We have inverse cosine of x dx. U is equal to inverse cosine. Then du, should have given myself more room, would be the negative 1 over the square root of 1 minus x squared. dv is equal to dx, so v is x. So this is equal to u times v, x, arc cosine of x, minus the integral of v du. So we have x times inverse cosine of x. I have minus minus, so that's really just plus. I'm going to write this as x, and I'm going to write this as 1 minus x squared to the minus 1/2 power. Now, I have a brand new u because I have to u substitute in order to do this piece. Not at all related to that u. U is equal to 1 minus x squared. du is negative 2x. dx over negative 2x over negative 2x. So this guy doesn't change at all. I have the integral of x u to the minus 1/2, and then instead of dx I have du over negative 2x. So that x cancels with that x. I have x inverse cosine of x minus 1/2 comes out in front. I add 1 to the exponent, divide by the new exponent. So u to the positive 1/2 over 1/2 plus a constant. So that cancels with that. And I end up with x inverse cosine of x minus u to the 1/2, and u is 1 minus x squared plus a constant. So we had straightforward integration by parts. We had integration by parts, which were kind of disguised because it didn't really look like a product. This one we have a product. So let's let u be equal to t squared. Easy to differentiate. Du would be equal to 2t dt. dv is e to the t. So v is e to the t. And you notice I get kind of fast and loose about leaving off the dt's because I just get tired of writing them. So this would be equal to u times v, t squared e to the t, minus the integral of v du. I've got another product. I can do it again. Integrate by parts again. So again, u is equal to 2t. du is equal to 2 dt. dv is e to the t, so v is e to the t. So this is equal to t squared e to the t minus, have to be careful with your signs here, u times v, so 2t e to the t minus the integral of v du. So I have t squared e to the t minus 2t e to the t. I have minus minus, so plus 2 e to the t, because the antiderivative of e to the t is e to the t, and then plus a constant. Now, that wasn't too bad. I only had to do it twice. Suppose you had t to the 17th power sitting there. Oh, surely there's an easier way. There is. It's a table. So I'm going to redo this problem using what I call the table method. So we have the integral of t squared e to the t. I make 3 columns. A column for sine, a column for u, and a column for v. So my sign is always going to be plus, minus, until you run out. Your cue for when you use a table method is when you have a polynomial times either an exponential or a trig function. Something that's easy to take the antiderivative of. So, you write down your u and then you differentiate until you can't differentiate anymore. 2t, 2, 0. I have 0, I'm done. Now I'm going to start with my dv, which is e to the t. So my first v is e to the t, e to the t, e to the t. Then we circle. Remember, your first thing is u times v, and the first thing you wrote down was dv, so that's your first v. Here's your next u, v, and, whoops, your final UV. So your answer is positive t squared e to the t minus 2t e to the t plus 2e to the t. Exactly what we got. So again, you don't have to use a table method, but if you have a polynomial times an exponential or a trig, it works really conveniently. So there's the pretty answer. There's the pretty answer using a table. And now do practice number 3, and then we'll come back and compare. Now, if you would like to choose U and dV 5 times, go right ahead. I did it using a table just because it made it really easy. So I had x to the 5th minus 3x plus 4. I differentiated until I got to 0. My first dV was cosine of 2x. Now it's not quite as simple because I had this coefficient in here. It made it a little more complicated, so that's okay. I had my table to help me. So the antiderivative of cosine of 2x would be 1/2 of the sine of 2x. Then when you take the antiderivative of sine, remember the answer has a co, so it gets a minus. And then you take the antiderivative of minus cosine, you get minus sine, etc. And yeah, I could have simplified. I could have made this a plus. I could have pulled the 1/4 out front. I could have rewritten this as minus 20 over 8, which would be the same thing as minus, let's see, 5 over 2. I'm not real interested in knowing that you know how to do arithmetic. I want to see that you know how to do the calculus part. So, table comes in handy when you have something that you're going to have to do integration by parts over and over again. Now, this one looks kind of like that, and you have two things that are really easy both to differentiate and to integrate, but these are the ones that are the most complicated. They're called loopy examples because they kind of loop back onto themselves. So let's look at example 4. We have e to the x sine of x dx. Now, here I let u be equal to e to the x. So I'm going to let u be equal to sine of x just to prove to all of us that it doesn't matter which way we do it. I'm going to let u be equal to sine of x. Then du is equal to cosine of x. dv is e to the x, v is e to the x. So this is equal to e to the x sine of x minus the integral of v du. Well, darn. We have to integrate by parts again, and the table method isn't going to work because nothing disappears. You'll never get rid of all your e to the x's and all of your trig functions. So we'll do it again. Let u be equal to cosine of x. Then du is negative sine of x. dv is e to the x. V is e to the x, and let me put an arrow in there just to be consistent because I hate it when I'm not consistent. So e to the x sine of x minus, and put a big pair of brackets to make sure that I know I'm replacing this integral with u times v, so cosine of x e to the x, minus the integral of v du. So now I'm going to get rid of that big set of brackets. This is equal to e to the x sine of x minus e to the x cosine of x. I just switched those directions. I have minus, so that would be plus, but I have a minus outside here, so this is minus the integral of e to the x sine of x dx. So this is equal to all of this. Let's add the integral of e to the x sine of x to both sides. So 2 integral e to the x sine x dx is equal to e to the x sine of x minus e to the x cosine of x. Well, my goal was to figure out what just plain old integral was. So the integral of e to the x sine of x dx is equal to 1/2 of e to the x sine of x minus e to the x cosine of x. And at some point you need to add c in there. Loopy. It loops back on itself. Make sure I have it right. And there's the pretty answer. I have minus e to the x cosine of x, e to the x sine of x. And you notice I got the exact same thing when I did it, starting with u as e to the x, as when I let u be equal to the trig function. So here's another one, and you notice it's going to be a little more complicated because it has that coefficient sitting next to theta. So I'm going to take a break and do it off camera, then we'll come back and compare our answers. Okay, I went to the back of the page so I wouldn't have to flip back and forth in the middle of the problem. I let u be equal to cosine. You could just have easily let u be equal to e to the negative theta. I did it so I wouldn't have to deal with fractions, because I knew that if I did the antiderivative of cosine of 2 theta, it would be 1/2 sine of 2 theta. So I just did it so I could play with whole numbers instead of fractions. You're going to end up with a fraction at the end anyway, because you end up with 5 times this integral here. But I did my u, my dv. I went ahead and took another row to write down negative times negative gives me positive, so I have negative, and I pulled the 2 out front. So then I just look at this piece to do the integration by parts with. I let u be equal to the sine and dv be equal to e to the negative theta. So then I did my big brackets. I put the negative 2 outside and replaced just this integral with uv minus the integral of v du. Again, I simplified it as much as I could. I distributed that 2. Minus times minus gives me plus. Minus times plus. And I pulled the 2 times 2, which is 4, out front. Then I added 4 times that integral to both sides, gave me 5 times the integral, and then I divided both sides by 5, and I ended up with my final answer. And I did not forget to add c at the end. The final thing we're going to look at is integration by parts for definite integrals, and it works just like you expect it to. If you want, you can just go to the side and do all your integrating and then do your substituting at the end. That is fine. I'm going to take a minute and write this one down. So, doesn't look like a product, but it's an inverse trig function, which means I can use integration by parts by letting u be equal to that inverse trig function. Then du would be equal to dx sitting on top of 1 plus x squared. dv is equal to dx, which means v is equal to x. So, I have u times v, so I'm going to go ahead and write it as x times inverse tangent of x. That needs to be evaluated from 0 to 1, minus the integral from 0 to 1 of v du, which again we notice we're going to have to do u substitution with a different u on this one. So let's go ahead and just leave this as x times inverse tangent of x evaluated from 0 to 1. I'm going to let my new u be equal to 1 plus x squared, then du is 2x dx over 2x over 2x. U evaluated at 0 would be equal to 1, and u evaluated at 1 would be 1 plus 1 squared, which is 2. So this would be minus the integral from 1 to 2 of x sitting on top of u times du sitting on top of 2x. So that goes away with that. Now I'll go ahead and start plugging stuff in. I'll plug my 1 in, 1 times the inverse tangent of 1 minus 0 times the inverse tangent of 0. That takes care of that piece. Now remember, I updated my limits of integration, so my x does not need to come back. I'll pull the minus 1/2 out, and I have du over u, so that's just the natural log of the absolute value of u evaluated from 1 to 2. So 1 times the inverse tangent of 1 is pi over 4. 0 times the inverse tangent of 0 is 0, minus 1/2 of the natural log of 2, but the natural log of 1 is 0. So I end up with just pi over 4 minus half of the natural log of 2. And here's my pretty answer. And here's another one to try. So I'll work on this one and then we'll compare our answers. Okay, so I let u be equal to 5t. Then du is 5 dt. dv is my trig function. Easy to take the antiderivative of cosine. It's negative sign. And since it was 2t, we divide by a 2. So I'm careful with my signs. U times v minus the integral of v du. I went ahead and plugged in my 2 pi. Cosine of 4 pi is equal to 1. But since I plug in 0, 0 times anything is 0, so I'm left with this piece. And then when I do the antiderivative here, I have the sine of 2t over 2, and I expect you're a savvy enough mathematician to know that the sine of 0 is equal to 0, and the sine of any multiple of 2 pi is equal to 0. So all of that part just goes to 0. So our final answer is minus 5 pi. Practice these. Look for the patterns. You can do this.